41. Light years from where you are sitting right now, there's a small rocky world so close to its star that it finishes an entire orbit in about 18 hours, dragging its permanently molten dayside through a continuous wall of stellar radiation. Astronomers have been arguing about what that world looks like for almost 20 years. This year, the James Webb Space Telescope finally pointed at it the right way, and the data that came back broke nearly every major model that had been built. To explain the place, so today I want to walk through what 55 Cancri A actually is, why Webb's latest look at it contradicts more than a decade of confident forecasts, and what that contradiction says about how rocky planets like the one we live on either survive or get stripped down next to their stars. Before we go further, a quick note on how this channel works. We try to go slowly, on purpose. The story of Webb and 55 Cancri E is genuinely strange, and there is a real temptation in coverage like this to skate past the parts that don't fit easily into a punchy headline. If the kind of patient, fact-first coverage of space and Earth system stories is what you actually want in your feed, the easiest way to keep getting it is to subscribe. There are more of these stories in the pipeline, and they are getting stranger. Let me start by putting the planet on the map. 55 Cancri E orbits a sun-like star called 55, Cancri A, in the constellation Cancer. The star sits at the edge of naked-eye visibility from a dark sky, which is unusual for a star that hosts a famously interesting planet. The system is only about 41 light-years away, which makes it one of the closest known rocky exoplanets of its size, class to Earth. The planet carries an official name now, too. In 2015, the International Astronomical Union approved the name Janssen for it, after the 17th century Dutch spectacle maker Zacharias Janssen, in keeping with a broader tradition of giving names to exoplanet systems around bright stars. 55. Cancri E was first detected in 2004 using the radial velocity method, which is a fancy way of saying astronomers watched the star itself wobble. When a planet orbits a star, the planet's gravity tugs the star very slightly back and forth, and that motion shifts the wavelengths of the star's light toward the red and then toward the blue in a rhythm that matches the planet's orbit. Back in 2004, that wobble was enough to give a tentative mass for the new planet, but not enough to know anything about what the planet actually looked like. In 2011, astronomers finally caught the planet transiting its star. A transit is just the planet's silhouette crossing in front of the star's face, dimming the star's light by a tiny but measurable amount every orbit. Once that transit was confirmed, suddenly the planet's radius became known, and its density could be calculated. The planet turned out to be about 1, and a half times the radius of Earth, with roughly 8 times Earth's mass, which is exactly the definition of a class astronomers call super-Earths. They are bigger than Earth, smaller than Neptune, and almost certainly rocky rather than gaseous in composition. Now here's the detail that makes 55 Cancri E genuinely unusual. It orbits its star at a distance of about 2.25 million kilometers, which is roughly 1/25th of the distance between Mercury and our Sun. At that orbital radius, the planet completes a full lap in only about 17 hours and 40 minutes. Our closest planet, Mercury, takes 88 days to do the same thing. Earth, obviously, takes 365. The year on 55, Cancri E is shorter than a single Earth day. That is the headline number. Everything else flows from it. A planet at that distance earns something else. The same gravitational pull that locks the moon's near side permanently toward Earth also locks 55 Cancri E toward its star. The planet is almost certainly tidally locked, with one hemisphere permanently facing the star and the other permanently facing away. The day side gets cooked continuously. The night side gets no starlight at all. Between those two halves is a thin belt called the terminator, where day meets night. Early consensus on the planet imagined a globally molten magma ocean covering the day side, with perhaps a thin, wispy veil of vaporized rock above it. Rock essentially boiled off the surface by the heat, condensing briefly before falling back into the magma. No real atmosphere in any traditional sense, just rock traversing its gas phase. For a long stretch, that was the textbook mental image. There were a few variations on the theme. One early suggestion, based on estimates of the planet's density, was that 55 Cancri EA might be a so-called carbon planet, a world with so much carbon in its interior that huge portions of it might be compressed into something resembling diamond under the enormous internal pressures. That idea made for fun headlines. Subsequent observations have largely pushed it aside, but the more important takeaway from that episode is that scientists were genuinely uncertain about what this planet was made of, not just whether it had an atmosphere. There was not much solid ground to stand on. So the situation by early 2024 was this. Spitzer Space Telescope data, taken before Spitzer retired, suggested a thick, volatile atmosphere, but Spitzer's instruments could not separate that signal from the alternative possibility of bare rock under a thin mineral vapor. 2 decades of work had not produced a clean answer. A new instrument was needed. This is where the James Webb Space Telescope comes in, and where the story starts to change direction. Webb launched in late 2021 and began science operations in 2022. For a planet like 55 Cancri E, Webb's 2 main instruments are the relevant tools. The first is NIRCam, the near-infrared camera. NIRCam is good at picking up relatively short wavelength infrared light. The second is MIRI, the mid-infrared instrument, which sees longer wavelength infrared. Light that is especially good for measuring the actual temperature of warm or hot things from their emitted heat. To study 55 Cancri E, the team led by Renyu Hu of NASA's Jet Propulsion Laboratory used a technique called secondary eclipse spectroscopy. The idea is clean. The planet does not directly face us in a static image. It just orbits and disappears periodically behind its star. When the planet is beside the star in our line of sight, the telescope sees starlight plus planet light combined. When the planet slips behind the star, the telescope sees starlight only. The difference between those 2 measurements is the planet's own light. Subtracting one from the other and spreading the resulting light across its wavelengths gives a thermal emission spectrum, basically a fingerprint of the planet's heat and, crucially, of any gases in its atmosphere that absorb specific wavelengths of light. Hugh's team used NIRCam observations from November 2022 and MIRI observations from March 2023 to build that spectrum across wavelengths from about 4 to 12 microns. They published their results on May 8, 2024 in the journal Nature. The paper's title is unusually direct. It calls the result best evidence for a secondary atmosphere on the rocky exoplanet 55 Cancri A. So what did they actually find? There are 2 pieces, and the second piece is even stranger than the first. The first piece is a temperature discrepancy. If 55 Cancri A were truly bare molten rock under a thin mineral vapor with no substantial atmosphere to move heat around, the dayside temperature should reach roughly 2200 degrees Celsius. That is what you get when dark rock absorbs full sunlight with nothing to redistribute the energy. Instead, MIRI measured a dayside temperature of about 1540 degrees Celsius. That is still brutally hot. It is well above the melting point of almost every silicate rock on Earth. But it is several hundred degrees cooler than the bare rock model predicts. There's only one general way to explain it. Something on this planet is moving. Heat from the dayside toward the night side faster than molten rock can. The most likely candidate for that? Something is a real atmosphere of gases, not just rock vapor. The gases absorb heat on the dayside, flow around the planet, and release some of that heat on the cooler night side. The second piece is in the NIRCam data. The team saw a clear dip in the spectrum between 4 and 5 microns. That dip in the planet's emitted light tells you that something is absorbing light in that specific wavelength range. The only sensible candidates in the temperature and pressure range expected here are either carbon monoxide or carbon dioxide, both of which absorb strongly in that window. A bare rock surface, or thin mineral vapor, would not produce that specific feature. The dip is the chemical fingerprint. The atmosphere is doing something specific and verifiable. This is the moment where the entire prior model of 55 Cancri E starts to crack. A real atmosphere made of carbon-bearing gases has to be replenished somehow. The original hydrogen and helium that most rocky planets gather during formation would almost certainly be gone by now, blown away by the unrelenting stellar wind and heat from a star this close. The atmosphere Who's team is looking at has to be secondary, meaning it has come out of the planet itself since then. The planet is actively outgassing. The magma ocean below is releasing dissolved gases, and those gases are wrapping the planet in an envelope that, against all reasonable expectation, is still hanging on under conditions that should have stripped it bare years ago. Let that sink in for a second. 41 light years away, a world so close to its star that a full orbit takes less time than an Earth day is still managing to wrap itself in gases that bubble out of its own molten interior. The star has been bombarding that surface with heat and radiation for the entire history of the planet. Yet, in the present moment, there is still an atmosphere. That one fact alone reshapes how we think about the boundary between worlds that hold onto their air and worlds that lose it. Now, what makes 2024 and 2025 particularly interesting is that the story does not stop at one convincing measurement. There have been several follow-up studies since Who's paper landed, and they have not all agreed. In September 2024, a separate team, led by J.A. Patel, published a paper showing that the planet's brightness temperature at 4.5 microns is highly variable across repeated observations, swinging between roughly 870 Kelvin and 2256 Kelvin. 870 Kelvin is about 600 degrees Celsius. 2256 Kelvin is about 1980 degrees Celsius. That is a huge spread for the same planet observed with the same instrument. It tells you that something on 55 Cancri E is changing over time, on timescales that are much faster than any geological process. One realistic scenario being floated is that the planet has a dynamic cloud layer, with mineral clouds condensing briefly out of the vapor above the magma ocean before raining back down and being replaced by fresh outgassing. The atmosphere is not a static blanket. It is something with weather, sets of molten rock clouds forming and dissipating on timescales of hours. That would also explain why median dayside temperatures come in lower than the bare rock prediction. Bright mineral clouds reflect some starlight back into space before it can hit the surface, which cools the dayside atmosphere without any actual redistribution of heat required. A different kind of follow-up was published in 2020 by a team led by Emma Zlinskas, building on the same JWST observations. That team ran more than 25,000 different one-dimensional atmospheric models through a forward modeling grid, varying the assumed chemical composition and pressure-temperature profile, and checked which combinations best matched the data. The models that fit best were atmospheres with significant amounts of nitrogen and carbon-bearing gases, with water vapor and sulfur dioxide also producing reasonable fits in some scenarios. Notably, these models are not all converging on a single answer yet. They are converging on a family of answers, all of which agree on the basic point that this planet has a real gas envelope and disagreement on the exact chemical mix. The honest scientific position right now is therefore something like this. The 2024 WHO paper established the planet almost certainly has a real atmosphere. The 2024 Patel paper established that whatever's happening on the dayside is highly variable. The 2025 Zelinskas paper narrowed down the plausible chemical composition, but did not settle on one. These are not contradictions. These are steps along the same path. Each study used the same underlying instrument, but looked at different aspects of the system. Each added a new constraint that future work has to respect. It is also worth pausing to clear up something that always gets confusing in coverage of discoveries like this. There is an enormous difference between what a press release headlines say and what the underlying papers are claiming. The WHO paper does not say definitively that this atmosphere will last forever or that we know its exact composition. It says that the data are consistent with a real volatile rich atmosphere. The atmospheric gases that best fit, the data so far are consistent with carbon monoxide and carbon dioxide with significant hydrogen, subject to additional confirmation. The headlines that say NASA confirmed Martian life just because today's NASA press release sounds confident should always be calibrated against the actual paper text. Now here's the broader point, and it is the one worth sitting with. 55. Cancri E is not the only lava world astronomers know about, and it is definitely not the only one Webb is now studying. Lava planets in general are a category that has gone from quirky curiosity to active frontier over the last decade. They tend to be tidally locked to their stars. They have permanent daysides with surface temperatures high enough to keep rock molten. Their orbits are typically ultra-short, meaning a year can be anywhere from a few hours to about a week or two. They are not habitable. Nothing like Earth biology could survive on them. But as natural laboratories for studying atmosphere formation on rocky planets, they are extraordinarily valuable. Earth, Venus, Mars, and probably Mercury all went through molten phases in their earliest history. We cannot go back in time to watch those phases. Lava worlds let us watch the equivalent process unfold right now. 3 other worlds deserve to be mentioned specifically. K2-141b is a rocky planet around the star K2-141 in our own galactic neighborhood, with a year lasting less than 7 hours. Modeling work published in 2020 suggested that its surface may be mostly ocean magma on the dayside, with mineral vapor atmosphere above and a rock vapor rain falling on the cooler terminator and night side. TOI 561b is an ultra-hot super-Earth, about 270 light-years away, with a year of roughly 10.5 hours. In December 2025, a team led by Johanna Teske published a paper in the Astrophysical Journal Letters using JWST observations that found evidence of a thick, volatile envelope above a global magma ocean on that world, similar in spirit to what WHO's team saw on 55 Cancri A. That is now 2 well-observed rocky worlds with real atmospheres in the same general regime, which means 55 Cancri E is at least starting to look less like an outlier. HD 63433 is a planet roughly the same size, younger, orbiting a young sun-like star that is still producing strong flares. It is the kind of world that lets astronomers see what early-stage rocky planets look like while the parent star is still active. The collection of these worlds gives astronomy something it has never really had before. Until JWST, most confirmed exoplanet atmospheres belong to gas giants. That made sense, because gas giants have thick envelopes that are easier to detect. Now, with the new spectroscopy, we are beginning to see rocky world atmospheres too. Some appear thick and stable, some appear thin and variable, and some do not appear to exist at all. Building that database is genuinely how we are going to figure out the conditions under which a small rocky planet either keeps its air or loses it. That is also where the comparison to a much closer body becomes instructive. Jupiter's moon, Io, is the most volcanically active world in the solar system. There are hundreds of active volcanoes across its surface, and its surface is constantly resurfaced by lava and sulfurous deposits. The driver, however, is completely different. Io's volcanism comes from tidal heating, the constant gravitational squeezing and flexing caused by Jupiter and Io's orbital neighbors, Europa and Ganymede. The flexing generates internal friction, and that friction generates the heat. Io is not being warmed mostly by the sun. It is being warmed mostly by its own orbit. 55. Cancri E is the opposite. It is not being flexed by a giant neighbor. It is being cooked directly by its star. Two intensely volcanic worlds, driven by two entirely different mechanisms, both producing molten surfaces and outgassing atmospheres. Astronomy has very few cases where two processes can be compared side by side on worlds of roughly similar size. This is one. Let me come back to the personal scale of this question for a second, because that is the part most coverage leaves out. The thing that Webb's 55 Cancri E observations actually mean is not that we found one weird planet. The thing they mean is that the line between planets with atmospheres and planets without is more porous than we thought. For most of the modern era of exoplanet science, the operating assumption has been that small rocky planets very close to their stars almost always lose their atmospheres. The star's radiation strips them bare. That is still often true. But 55 Cancri E shows it is not always true, and that the case where it is not true has a tidy explanation. Magma ocean, dissolved gases, continuous outgassing, replenishment of the envelope. That is a process that can, in principle, work on any rocky planet that has surface melting or that has internal heating to drive volcanic activity. Earth had it early, Venus probably had it, Mars might still have a weak version of it in isolated regions. The lava worlds of the galaxy are not just curiosities. They are showing us snapshots of what our own planet looked like in its first few 100 million years. Around the midpoint of this story, here is a quiet irony worth naming out. Loud. The same telescope that found water in the atmospheres of potentially habitable planets around small, cool stars like TRAPPIST-1 is now finding carbon-bearing atmospheres on planets that are absolutely not habitable. That is actually exactly how the science has to move. The instrument cannot know in advance what shape the answer will take. It just gathers better data than anything before it, and the answers fall out. Some of those answers confirm what we hoped. Some of those answers blow up what we assumed. Either way, they are real. Here is an open question I want to leave hanging for a moment, because it is going to come back around at the end. If 55 Cancri E can keep an atmosphere under those conditions, why couldn't TOI 561b? Or why is K2 141b so different from HD 63433d? Is it the star's magnetic field, the planet's mass, the depth of the magma ocean, the age of the system, the distance from the star by just a few extra percentage points? Each of these factors plausibly matters. None of them has been pinned down yet. When we eventually have an answer, it will probably be a list, not a single cause. That is how planetary science usually goes. The answer is rarely one neat mechanism. It is a stack of conditions, each one tipping the outcome a little. One more very common confusion to clear up. The transit method, which is what gave us 55 Cancri E's radius and confirmed its orbit, does not work for every planet. It only works for the small fraction of planetary systems whose orbital plane happens to line up almost exactly with our line of sight from Earth. Most planets do not transit. The radial velocity method, which gave us 55 Cancri E's mass and period in 2004, is much more broadly applicable because it does not require transit at all. It just requires the star to be bright enough and the planetary tug to be big enough to measure on a spectrograph. The combination of transit plus radial velocity is the gold standard because it gives both mass and radius, which gives density, which gives a real sense of what the planet is made of. Most of the most interesting exoplanet science over the last 2 decades has happened for planets that happen to fall into both categories. 55. Cancri A was one of the lucky ones. And now to the closing turn. Here is the strange thing about this story. A telescope that was built to look at the faint galaxies at the edge of the observable universe, galaxies so distant their light left them when the universe was only a few 100 million years old, is now making its biggest contributions to one of the smallest, hottest, strangest rocky worlds that we know about right next door. Webb was not designed for that. It was designed for the deep field, for cosmological first light, for understanding how the first stars and galaxies lit up. Instead, it has turned out to be extraordinarily good at teasing chemistry out of hot, faint, planet-sized heat sources against the relentless glare of nearby stars. The number of questions it has answered is dwarfed by the number of questions it has opened up. The list of worlds that now sit on the priority list for follow-up observation is essentially every ultra-short period rocky planet ever confirmed. The list of papers this one instrument will produce over the next several years is going to reshape atmospheric science on rocky worlds in a way that no single mission has done since the Voyager flybys taught us what the outer solar system's moons actually look like. The final piece to sit with is what this says about the future. We have spent 30 years confirming that planets orbit other stars. We have spent 20 years starting to characterize them. We are now, in a very real sense, only just beginning to ask the right questions of them. The question is no longer how many planets are out there. The question is what they are made of, what they are doing right now, what their weather looks like, what their interiors look like, what their atmospheres are made of, and which ones are even still in the running for habitability. JWST has turned those questions from theoretical to measurable. The answer for 55 Cancri E in 2024 is that this alien lava world, sitting in the worst imaginable spot for atmospheric stability, has an atmosphere made of outgassed gases. The next layer of the answer is that the atmosphere is changing on us. The layer after that is whether the change is weather, volcanism, or something else we have not yet named. Each layer pulls the picture out a little further. The deeper truth is that we are at the very beginning of seeing rocky planets as worlds with their own restless weather, rather than as inert balls of rock and gas orbiting dots of light. If the patient coverage of stories like this one is what you actually want to keep in your feed, the simplest way to lock that in is to be subscribed, because the next video in this series is going to take this whole question one step further. We are going to look at the small but growing list of rocky planets that are losing their atmospheres as we watch them, the ones where 55 Cancri's surprise is replaced by the opposite finding Butte. The atmosphere is genuinely gone, and what that comparison tells us about how rare planets like Earth actually are real, not just possible. There is more of this coming, and it is going to get more interesting, not less. Keep looking up. We will see you over there. Sources. Hu R. et al. A secondary atmosphere on the rocky exoplanet 55 Cancri A. Nature, May 8th, 2024. https www.nature.com. Articles is 41586-024-07432. X. Patel, J.A. et al. JWST reveals the rapid and strong dayside variability of 55 Cancri A. Astronomy and Astrophysics, 2024. https www.anda.org or articles A full HTML then 2024 10 I feel so 748 24 A but it was 748 24 HTML Zelinskas Motor al characterizing the atmosphere of 55 Cancri A 1D forward model grid for current and future JWST observations. Astronomy and Astrophysics 2025 https.www.anda.org articles AA full HTML the 2025 05 if AA 54062 25 A4062 25 HTML Loftus K et al. Extreme weather variability on hot rocky exoplanet 55 Cancri E 225 https.pmc.cbi.nlm.gov articles PMC 427 European Space Agency web press release May 8th 2024 https soweb.org news.week 24 mile NASA JPL press release on 55 Cancri E https www.jpl.nasa.gov.news NASA's web hints at possible atmosphere surrounding rocky exoplanet. NASA web release on TOI 561b https://science.nasa.gov missions. Web NASA's web detects thick atmosphere around broiling lava world in Dulcides. Teske JK et al. A thick volatile atmosphere on the ultra-hot super-Earth. TOI is 561b. Astrophysical Journal Letters 2025 https://iopscience.iop.org article 10.3847 241 8213 A04C Carnegie Science announcement on 2Y561b December 10th 2025 https://Carnegie Science edu ultra hot lava world has thick atmosphere upending expectations Wikipedia 55 Cancri AA https://nwikipedia.org Wiki 55's Cancri and